started. All right, let's continue. We have already discussed the life cycle of both human and mosquito life cycle of the Plasmodium. We have already covered this slide as well, so let's proceed to the next. The succeeding slides class of this presentation would be a reinforcement of the life cycle of the parasite, which we have already discussed on my previous lecture video. So, if you have already mastered or familiarized yourself to the processes, this would be easier for you to digest. The remaining slides would be easier for you to digest. Okay, so let's proceed. So let's start with the extrinsic incubation period. What is extrinsic incubation period? So it is extrinsic. Why extrinsic? It is termed as extrinsic because it is influenced by factors outside the human body, meaning this happened inside the mosquito. Since outside man, it's inside the mosquito. So this period, this extrinsic incubation period is the period when the mosquito becomes infected with the plasmodium and when it becomes infectious to humans. So this period is between the when the mosquito is infected with the plasmodium parasite and when it becomes infectious to humans. So this is basically the extrinsic incubation period. And again, this process takes place in the mosquito, specifically in the midgut. So if you have remembered our life cycle, in the midgut, that is where your plasmodium parasite undergoes several stages of development. Okay? So in simpler terms, class, after a mosquito bites an infected person and ingests the Plasmodium parasite, the parasite goes several stages of development inside the mosquito. And only after this development is complete can the mosquito bite another person and transmit the Plasmodium. So that is what the extrinsic incubation period is all about. And this varies depending on the species of your Plasmodium, as you could see here. So the temperature, the specific temperature, which is 25 degrees Celsius, also plays a very crucial role. So here's the time frame for the incubation period for each Plasmodium species. First one, we have here Plasmodium vivax. We have 8 to 10 days. If you have remembered, Plasmodium vivax is one of the most common malaria-causing species. Second to Plasmodium falciparum. So, after a mosquito ingests the Plasmodium vivax from an infected human, it takes 8 to 10 days for the parasite to mature inside the mosquito. And after this period, the mosquito becomes capable of transmitting the parasite. So meaning the mosquito now is now infectious. So that is for Plasmodium vivax. It took 8 to 10 days. 8 to 10 days for the parasite to mature inside the mosquito and become infectious. For Plasmodium falciparum, take note that your Plasmodium falciparum is the most dangerous and potentially the most fatal species of Plasmodium. So, for Plasmodium falciparum, it is slightly longer than your Plasmodium vivax. It takes 9 to 10 days. So, for Plasmodium malariae right here, among the four clinically significant species, Plasmodium species presented to you, Plasmodium malariae has the longest extrinsic incubation period and it takes about 25 to 28 days. So, this would only mean, class, that this longer incubation period means that the mosquitoes carrying Plasmodium malariae might take longer to become infectious. Okay? So it takes Plasmodium malariae 28 days to become infectious and infect humans. So we have here as well, last but not least, Plasmodium ovale. It has a moderate extrinsic incubation period compared to the three. So it is typically around 14 to 16 days. But while it is not as common compared to Vivax and Falciparum, please take note that ovale is still important. It still contributes to malarial infections. Okay, so and here we would be talking some of the processes that your plasmodium would undergo in the mosquito life cycle. Most of these processes are already discussed in our discussion about the life cycle. So first one, we have your exflagellation. So if you have remembered, your exflagellation refers to the process where the male gametes, male gametes of your plasmodium undergo a series of changes that would enable them to become motile. So only the male gametocyte would undergo the process of exflagellation. Okay, so the male gametes would undergo the process of exflagellation that would enable them to become motile and capable of fertilizing the female gametes right here. So take note that the male gametocyte is when it already undergoes flagellation, it will now become microgametes. Microgametes. Okay, please take note again, in parasitology, usually the males are smaller compared to the females. So therefore, your female gametocytes right here, when it undergo maturation, will now become macrogametes. Okay, please take note that your male gametocyte would undergo exflagellation and would become microgametes, while your female gametocyte would undergo maturation and would now transform to become the macrogametes. All right. So in the exflagellation right here, as you can see, these microgametes are actively motile since exflagellation, flagella. So they would undergo a process wherein their nucleus divides, and this division results in the formation of multiple smaller flagellated bodies called microgametes. So these are the microgametes right here. Okay, and they will be needing these microgametes for the formation of zygote. So if you have remembered, with the use of your microgametes, the microgametocyte is now motile, it would look for a female macrogametocyte. So when the female and male gametocyte would fuse, so or would undergo the process of fertilization, then there would be a process or there would be a product of zygote formation. So this zygote formation is again the product of the fertilization when your male microgametocyte meets up your female macrogametocyte. So when your female and your male gametocytes undergo the process of fertilization, there would be the formation of a zygote. So the gametes would fuse, creating a zygote. Please take note, class, that this zygote is non-motile. This is non-motile, huh? It is non-motile. So this non-motile, after fertilization, the zygote transforms to become the motile form. So this motile form can now move through the mosquito's midgut wall. And this motile form is what we call as the ookinete. The ookinete in some books is also referred as the traveling vermicule. Traveling vermicule. When you say vermicule, that means worm-like. So as you can see right here, Within 24 hours of fertilization, within 24 hours of fertilization, the zygote in this form, the zygote, which is initially again non motile and rounded, transforms to become a vermicular or worm like structure, elongated structure known as your ookinete. So this ookinete has an apical complex. If you have remembered, apical complex is for adhesion. Apical complex class is not just for adhesion, but it is also a specialized structure that would help move the ookinete through the mosquito's midgut wall. So what will happen? Your ookinete right here would actively travel through the mosquito's midgut wall using its motility, since it is already motile, to reach the basement membrane. So this is the membrane. So when it reaches the basement membrane, it penetrates to the stomach wall, and it would now cover itself with a very thin elastic membrane, forming an oocyst. An oocyst. Please take note that inside the oocyst, the parasite undergoes further development. Inside the oocyst, sporozoites are eventually developed. So inside the oocyst, we have the production of sporozoites. Okay? So oocyst now would undergo the process of sporogony or meiosis. So after meiosis or sporogony occurs inside the oocyst, the parasites again produces a lot of sporozoites inside. So again, your oocyst would undergo the process of sporogony or meiosis. So after sporogony happens inside the oocyst, the parasite produces sporozoites. If you have remembered, your sporozoites right here is the infective stage of the Plasmodium species. Your sporozoites has an anterior apical complex. It has an anterior apical complex that would help them invade the host cells. So take note that your sporozoites are motile. If you remember that one, your sporozoites are motile. It has an apical complex. It would help them invade host cells, and it would also help them move around. So the sporozoites migrate from the oocyst, from the stomach wall right here, to the salivary glands of the mosquito, where they are stored until the mosquito feeds on a human host. So, again, please take note that the sporozoites are the infective stage for humans. So, therefore, when an infected mosquito bites a human, it injects the sporozoites into the bloodstream, and the life cycle happens. So, once a mosquito is infected, please remember that once a mosquito is infected with the plasmodium, it remains infected throughout its life. So, meaning it is capable of transmitting malaria to humans in the future bites. So, if it is infected throughout its life. So, we're done with your mosquito life cycle. Let's proceed to the human life cycle. We already discussed the human life cycle. So let's just have a very quick review of your endogenous life cycle. And it starts with your mode of transmission. So the most common mode of transmission will always be the mosquito bite. But we have certain routes, which are the less obvious ways that Plasmodium species can spread. So, first thing here is the blood transfusion. So, just imagine this. If you're in a hospital and someone needs a blood transfusion. Now, if the donor has malaria, their merozoites, if you have recalled the life cycle, their merozoites are floating around in the blood. So when the blood is transfused into the recipient, those merozoites are ready to do their job. It would invade sa matalang job. What will be their job? They would invade the red blood cells, and of course cause malaria. So for your blood transfusion, the infective stage would be the merozoites. So that is why during blood donations, it is carefully screened for malaria to prevent this kind of transmission. Now, we have here another transmission, the transplacental transmission. So this is how it works. When a pregnant woman with malaria has merozoites in her blood, these merozoites can cross the placenta and infect the fetus right here. So this is called congenital malaria. And it can cause serious health problems for the newborn, like anemia. We have also low birth weight. So this is low cam baby. The baby is so low. Another one is your renal transplant or the donor transplant. So this is another route for malarial transmission. So if the donor's kidney is infected with malaria, the merozoites in their blood can be transferred to the recipient during the transplant. It's just the same um, explanation or pathophysiology of your blood transfusion. So just like in the blood transfusion, the merozoites are the culprits here. So they are the infective stage. So why are always the merozoites? So the merozoites are the infective stage of these situations because unlike the sporozoites, it needs a mosquito to deliver, 'di ba? So the sporozoites are from the mosquitoes. So the the sporozoites need a mosquito to deliver them, wherein the merozoites are already circulating in the blood. So they're just waiting for a new host to invade and start the cycle all over again. So if you go back to your life cycle, you know that your merozoites are the culprits. So there are the triggers. They would initiate erythrocytic life cycle. They would initiate intra-erythrocytic life cycle. They're the triggers of the disease or the infection. That is why in this mode of transmission, the life cycle or the infective stage of these mode of transmission will always be the merozoites. So in here we have the human life cycle. We have already discussed this one. Your human life cycle is subdivided into three stages. We have the pre-erythrocytic schizogony that happens in the liver, also known as your exoerythrocytic schizogony, also known as your hepatic schizogony, also known as your tissue stage. So those are the other names, or also known as your merogony. And next phase is your erythrocytic schizogony. So erythrocytic meaning it happens inside your RBC. And we have here, last but not least, we have the gametogony. So let's start with your pre-erythrocytic schizogony. So your pre-erythrocytic schizogony is also known as your exoerythrocytic schizogony, also known as your intrahepatic schizogony or intrahepatic tissue stage. It's just the same. So this is a moment where the sporozoites enter the liver. So if you have remembered and review your life cycle, once a mosquito injects the motile sporozoites into the bloodstream, these sporozoites quickly leave the circulation and enter the liver. So this class, by the way, the sporozoites enter the liver within 30 minutes. So within 30 minutes, it would enter the liver. So the circumsporozoite protein on the surface of the sporozoites would bind to the hepatocytes. So with the help of your apical complex and with the help of your circumsporozoite protein, it would bind to the hepatocytes. So or your liver cells. So this binding is very important to the parasite because it would begin its life cycle inside the liver. So if it won't bind to the to the hepatocytes, there's no life cycle to begin with. So right after inside the liver, what's next? So I want you to take a look of your notes. Okay, so this is a chance for you to master the life cycle. So once inside the liver, the sporozoites again transform to become the trophozoites, which are the feeding stage. the active stage of the parasite. So these trophozoites starts to consume nutrients from the liver cells, and the trophozoites would now transform to become your schizons, and the schizons would undergo hepatic schizogony. So this is a process wherein the parasite undergoes multiple rounds of nuclear division right here. So it would undergo nuclear divisions, so meaning it would copy itself, so schizons, and it would produce schizons. And the schizons would ready to transform to the next phase. So if there's schizons, the schizons would multiply inside the hepatocytes. And what will happen if the schisms would keep on multiplying inside the hepatocytes? The hepatocytes would eventually burst right here. So your hepatocytes would eventually burst, releasing your hepatic merozoites. All right. So it would release your hepatic merozoites. So what will happen in your hepatic merozoites? So your hepatic merozoites now is ready to invade your RBC and ready to start the phase 2 of your life cycle. So take note here, class. We have here some series of characteristic feature of your Plasmodium species. But before that, please remember that not all liver cells are infected by the Plasmodium. Okay? Not all liver cells. So in fact, only a few hepatocytes are affected, which is why hepatic damage is not as severe compared to um, what happened to your RBC, where there is RBC lysis. So there, the damage is not as severe compared to your RBC. So basically, your liver can typically handles the infection without significant damage. So in here, um, please take note as well that some sporozoites of your Plasmodium vivax and your Plasmodium ovale don't fully develop right away. Okay, so they don't fully develop right away. Instead, most of them remain in the dormant stage inside the liver, and this is known as the hypnozoites. So these hypnozoites, going back right here, this hypnozoites can stay there for years. So they would stay there for years before becoming active again and cause a relapse of malaria. So this is different from what we see in Plasmodium malariae and Plasmodium falciparum, huh? Because your Plasmodium vivax and Plasmodium ovale is responsible for the relapse infection, while your Plasmodium malariae and Plasmodium falciparum, where the infection doesn't relapse but may come back due to recrudescence. So, what is recrudescence? This is the reappearance of the infection due to parasites' ability na it didn't fully clear from the body. So, we will talk more about that later. So, in here, as the parasite continues its life cycle, the pre-erythrocytic schizont formed after the schizogony here will ruptures, ruptures, it would release the merozoites. And these merozoites again are released and enter the bloodstream, where they will invade the RBCs and continues the life cycle of the malaria. So here, this is what actually happens here. So we have here some characteristic features of the duration of the pre-erythrocytic schizogony. But what I want you to focus on is this one, the number of merozoites per infected pre-erythrocytic schizont. As you can see, Plasmodium falciparum has the most merozoites that could infect a pre-erythrocytic schizont, and that would really tell you that Plasmodium falciparum can cause severe destruction of the RBCs and can cause severe malaria compared to these three right here. Okay? So this is what I've been telling you a while ago. This is the differentiation between relapse and recrudescence. We have already discussed this during the face-to-face lecture. So let me just review of this types of infection. So when you say relapse, this is very common again to Plasmodium vivax and ovale. So this is very common to vivax and ovale infections. This happens, relapse infection happens due to the presence of hypnozoites. Therefore, hypnozoites initiates the relapse infection. So if you remember, a few sporozoites fail to develop, specifically your bradyzoites fail to develop into pre-erythrocytic schizons and trophozoites, and instead it remained dormant in the liver as hypnozoites. Okay? So these hypnozoites can remain dormant for anywhere from 3 weeks to 1 year. And after this dormant period, the hypnozoite would be reactivated. So after this dormant period, the hypnozoites would reactivate, triggering the erythrocytic cycle and causing a relapse of malaria. That is why it's relapse. Okay, how about the recrudescence? Recrudescence, on the other hand, is seen in Plasmodium malariae and Plasmodium falciparum. So in Plasmodium falciparum infections, recrudescence occurs due to drug-resistant parasites that survive treatment and continue to cause symptoms. So this is even after completing the prescribed treatment, the the parasites remain resistant. So that is what we call as recrudescence. In Plasmodium malariae, on the other hand, recrudescence happens because the erythrocytic stages of the parasite can survive in the bloodstream at low, undetectable levels. Meaning, even after a long time, Plasmodium malariae can survive in the bloodstream, undetectable. So these parasites can persist up to 60 years without being detected, only to reappear later when conditions may allow. So, what are these conditions? So, same story. If the patient is suffering from immuno um, compromise, or if the patient is immunocompromised or suffering from autoimmune diseases. So, this the difference between your relapse and your recrudescence infection. Again, relapse, very common to Vivax and Ovale. So hypnozoites remain dormant in the liver, and when reactivated, they cause a relapse infection, and this may happen weeks to years. While your recrudescence is very common to malariae and falciparum. When you say Plasmodium falciparum recrudescence infection, this persists due to drug resistance, while your Plasmodium malariae survives in low levels in the blood for decades, up to 60 years. So that is the main difference between these two infections. Okay, going back. So we have here the erythrocytic schizotony. So this happens when your merozoites attack on your RBC after the pre-erythrocytic schizont ruptures in the liver. So if you remember, when the pre-erythrocytic schizont ruptures in the liver, it releases merozoites into the bloodstream. So these merozoites are the form of the parasite that will invade the red blood cells. So remember what I told you, that the merozoites are usually the culprits for invading red blood cells. Therefore, they're also the same culprits where if the patient, when the patient can transmit the malaria to another human patient or human host. So it will always be the merozoite. It is the infective stage for blood transfusion, organ donation or organ transplant, transplacental. It's the merozoite. So again, so the merozoites, so these are the morphologic stage of the plasmodium that will invade the red blood cells and continue the life cycle. So aside from that class, the merozoites are has a specific target. So The merozoites specifically target RBCs, but merozoites specifically target glycophorin receptors on the surface of the RBCs. So if you remember, I told you about these receptors. So glycophorin, which is the receptor, is a protein that is actually found on the RBCs. So if this is your RBCs right here, there are receptors, and it would act as a docking site for the merozoite. So the entry of the merozoite into the RBC is a very quick process. It takes about 30 seconds. That is why you can't see the merozoites inside the RBC during PBS, on the PBS. So it takes about 30 seconds for the merozoites to enter the RBC, and it binds to the glycophorin receptors. So when the merozoite enters the RBC, the merozoite undergoes a transformation. So this early transformation is what we call as the early trophozoites. So your trophozoites has two maturation series. We have the early or the young trophozoites, and we have the mature trophozoites. So once inside the RBC, the merozoites transform to become early trophozoites. What is presented on your screens or an example of an early trophozoite, or what we call as the ring stages. So this is the first stage of the parasite's asexual reproduction inside the RBC. So the early trophozoite right here has a very distinctive appearance. It is often referred as the annular or signet ring form. So this form features right here a central vacuole in the middle. This is a central vacuole, a peripheral thin rim of cytoplasm, and then the nucleus, which is visible, often located at the edge of the ring. So this is this one, the nucleus. Okay, so please take note, class, that the ring form or the early trophozoite or the young trophozoite is the first asexual stage of the parasite that can be seen in the peripheral blood. Again, the ring form is the first or the earliest asexual stage of the parasite that can be seen in the peripheral blood. So during PBS, the youngest, the earliest, the first stage that can be seen will always be the ring form. And it is very important for diagnosing malaria since it is one of the key stages observed during the blood smears. This one. So in front of you on your screen, since this is an example of a ring stage, can you give me what plasmodium this is? Identify the plasmodium species. Your clue is multiple infection. This would be Plasmodium falciparum. Hope you got it right. Okay, so when the Plasmodium parasite invades the red blood cells, it starts breaking down hemoglobin. Remember that when your merozoite transforms to become a trophozoite, your trophozoites are the active and the feeding stage. So what it feeds? So it actually feeds hemoglobin. So it breaks down hemoglobin. So if you remember again, your hemoglobin is the protein in our blood that carries oxygen. Oxygen. So, but please remember that not all hemoglobin gets digested. So if you remembered, we have the undigested hemoglobins. So not everything gets digested. Some byproducts of hemoglobin, like we have here the hematine, the excess proteins, the iron porphyrin, don't get fully broken down. So instead, they would accumulate inside the parasite and form a pigment. And that pigment is what we call as the hemozoin. So what does hemozoin look like? So this is what hemozoins look like on your screen. So the pigment usually appears brown black. So kind of like little dark specks or granules inside the infected RBCs. This one. And here's where it gets interesting class. Why? Because in Plasmodium vivax, the pigment is a bit different. It has a yellowish brown. So this is actually a clue to identify this species. And in Plasmodium falciparum, the pigment is lesser. So you will find only a few granules in the infected cells. So why does hemozoin matter? Why should we care about this pigment? Well, hemozoin is not just a byproduct. So as medtechs, it is also our key diagnostic feature. So when we look at blood smears, the color and the quantity of the hemozoin actually help us figure out which type of plasmodium is causing the infection. So it's just like a biological fingerprint for the parasite. So if you see this, you would have a clue if what plasmodium species is infecting the patient. So right after that, um, we are already done with our young trophozoite or the early trophozoite. So let's now proceed to the late trophozoite and the erythrocytic schizon. So these life stages are also important of the asexual reproduction of the parasite inside the RBCs. So what we have here is the late trophozoites. As you have seen, this is an example of your late trophozoites right here on your screens. So the late trophozoite starts when the ring stage or the young stage of the parasite, which we saw earlier, this one, this one, which we saw earlier, becomes more irregular and enlarge. So this is your early stage of trophozoite or your ring form. And as you could see here, it begins to enlarge. So as it grows, the plasmodium becomes more irregular in shape. You would see that and appreciate that in your Plasmodium vivax. We have also here your malariae. So it becomes more irregular. Why is that so? Because it would change its shape. So it would become larger. So it would become more irregular in shape due to the amoeboid movement. If you have remembered, your trophozoite stage is the active stage. It's the motile stage. So it actually moves. So think of this as the parasite stretching. It stretch, it stretches and becoming less round and more like a blob. Oh, it's look like a blob. So this is actually a key point in the plasmodium's development as it prepares to move into the next stage. So when it becomes larger, so it enlarges, it would now become mature and it would now transform to what we call as the erythrocytic schizon. So at this stage, the trophozoites become more compact, as you could see here in the schizons. The trophozoites would become more compact. The vacuoles, the empty spaces within the cell, Ganesha, this one, the vacuoles would disappear and the pigments would start to scatter. It would start to scatter throughout the cytoplasm. This is your cytoplasm right here. It would start to scatter. So the nucleus of the parasite becomes also larger. It would become larger and moves towards the periphery of the cell. So in this stage, during the schizon stage, schizogony happens. So schizogony happens here, which is the process of your nuclear division. So if you remember that, the nucleus divides, it multiplies, and then there is a production of more merozoites inside the schizons. So when the schizons burst, the merozoites would be released into the system. So the merozoites here are the new infectious forms of the parasites that would eventually burst of the red blood cells to infect more cells. Okay, so in here you can see the merozoites. So these are the merozoites that form in the inside the mature schizons. So it would actually vary across different Plasmodium species. So in here, the number of merozoites produced by a mature schizont depends on the Plasmodium species. And here's a very quick breakdown. We have the Plasmodium vivax, which produces 12 to 24. We have Falciparum, that would be 18 to 24. Malariae, that would be 6 to 12. Ovale, 8 to 12 merozoites. As you could see, among the four Plasmodium presented to you, Falciparum has the most number of merozoites. That would really tell you that Falciparum has a lot of merozoites that can reinvade new RBCs. So these merozoites are the next generation of parasites, and each one of these merozoites is capable of invading new RBCs to continue the intraerythrocytic life cycle. Right? If you have remembered a while ago, we discussed about the intraerythrocytic life cycle. So, once the merozoites are released from the ruptured schizont, they invade new RBCs. So, this cycle repeats itself with the merozoites transforming into new trophozoites and eventually into schizonts again, and leading to the reproduction of more merozoites. So, that is your intraerythrocytic life cycle. Again, your intraerythrocytic life cycle, this is the moment when the merozoites are released from the ruptured schizont, going back to your life cycle, and this cycle repeats itself. So, from the merozoite, it transforms to become new trophozoites and eventually to become schizonts again and leads to the reproduction of more merozoites. So, for Falciparum, Vivax, and Ovale, right here, Vivax, Falciparum, Vivax, and Ovale, this repeats every 48 hours. So this repeats every 48 hours. For Nolasi, it repeats every 72 hours. For Nolasi, it repeats 24 hours. So, in short, your Falciparum, Vivax, and Ovale has the same malarial periodicity, if you remember that one. Diba? Tertian malaria. For malariae, Plasmodium malariae, the cycle repeats every 72 hours, meaning it's quartan malariae. For Knowlesi, it repeats every 24 hours. So therefore, it is quotidian malaria. So and every time the RBC would burst, the patient would also suffer from paroxysm. So that would actually tell you that the patient would experience a fever once in every 48 hours for falciparum, and once in every 72 hours for malaria, and once in every 24 hours or every single day for Knowlesi. Okay, so that is how our intraerythrocytic life cycle happens. So, and here, we have the incubation period for the different Plasmodium species. We have a special feature for Plasmodium falciparum. So, by the way, what is incubation period? So, this is the answer of how long before the symptoms will show. So, after a mosquito bite, how long does it take for the malaria parasite or the Plasmodium to make you feel sick? So that is the incubation period. So the typical incubation period for Vivax would be 14 days, but it can range from 8 to 17. So for falciparum, this one is usually 12 days, but it can range from 9 to 14 days. Malariae, this one's a bit of slow. So it has an incubation of 28 days and it can go as long as 40 days. We have Ovale. It's 17 days, but it's pretty narrow range of 16 to 18 days. So we have here malaria that has the longest incubation period. Now, here's where things gets interesting because your Plasmodium falciparum has a sneaky trick. So with this Plasmodium can do their thing in the blood and has a tendency to hide out in the capillaries of the brain and internal organs during the later stages of its life cycle. So your Plasmodium falciparum has the tendency to hide out in the capillaries of the brain and internal organs during the later stages of the life cycle. This is why when you look at a blood smear under the microscope, you'll only see the ring forms of Plasmodium falciparum in the peripheral blood. The mature forms, which are the trophozoites and the schizons, are hiding deep inside the organs, which make it harder to diagnose and more dangerous. So, if you have seen a PBS of a Plasmodium falciparum infection wherein you could observe mature forms, that would actually tell you that the patient is suffering from the severe form of malaria. So, severe form of Plasmodium falciparum infection na siya if you have seen the mature forms and the PBS. Because usually, when you look at your blood smear, you'll only see the ring forms of Plasmodium falciparum in the peripheral blood smear in the ordinary malarial infection. But if it's the severe form of Plasmodium falciparum, usually the mature forms are all already seen as well in the PBS. Why again? Because your Plasmodium falciparum has the tendency to hide out in the capillaries. So if it is in its mature form, it would hide out in the brain and internal organs during the later stages of its life cycle. So this severe complications would lead to cerebral malaria, which is eventually life-threatening. So that is how your sporozoites, or sorry, your Plasmodium falciparum life stages happen. So it would differ from, it would depend on the level of infection that the patient is actually suffering. So normally here, merozoites enter the red blood cells and turn into the trophozoites. But some will instead develop into gametocytes and would undergo the last phase of the human's life cycle, which is gametogamy. So these gametocytes are important because they are the form that can be taken up by a mosquito continuing the life cycle. So if you remember, gametocytes are the infected stage of the mosquito. So gametocytes right here are typically round, as you could see. They are typically round, but there are special characteristic for Plasmodium falciparum. So instead of being round, the gametocytes of your Plasmodium falciparum are crescent in shape or banana shape. And this would make them easier to identify during microscopic observation or examination. So again, there are two types of gametocytes. We have the microgametes and the macrogametes. So microgametes again is the male. So usually the male are shorter, smaller, and fewer in numbers. Again, in parasitology, usually the males are shorter, smaller, and fewer in numbers. And in this case, the microgametes are pretty distinct. So when they are stained, they have a pale blue cytoplasm. They have a pale blue cytoplasm and a large red diffused nucleus in here, male. So unlike the female, so diffused nucleus. But class, during in an actual clinical setting, you are actually not obliged to differentiate or identify or specify if it is a female gametocyte or a male gametocyte during your real clinical setting. It's not, medtechs are not ought to identify which is the female or the male. It doesn't matter anymore. But in here, for lecture purposes, so This is how we are going to identify them. So what we have here again, your male microgametocyte have a pale blue cytoplasm, and a large red diffuse nucleus. While your macrogametocyte right here, compared to your male, there are more numerous, so and much more abundant. So more numerous, much more abundant, and they are larger. So when stained, they have deep blue cytoplasm, as you can see. Deep blue cytoplasm and a small red but compact nucleus. Unlike here, we have your diffuse nucleus. Here we have red compact nucleus, and these are your female gametocytes or gametes. So please remember that gametocytes again are very important. So there are the key to sexual reproduction in the mosquito. So this is where the male and female gametes will fuse to form a zygote and continuing the life cycle of the parasite. So that is why they are very, very important. So let's take a look at when gametocytes first show up in the bloodstream after the asexual forms of the parasite start their work. So this is actually a key part of your malaria life cycle. So remember, these forms don't make you sick. Again, even if you have this, these morphological stages don't make you sick. So appearance of gametocytes in here, timing is really everything. So for Plasmodium vivax, gametocytes show up 4 to 5 days after the asexual forms begin their cycle. For Falciparum, the gametocytes appear a little later, 10 to 12 days uh, after the asexual forms start. We have Plasmodium malariae. For this species, gametocytes appear 11 to 14 days after the asexual forms. We have Plasmodium ovale. Gametocytes are seen 5 to 6 days after the sexual forms. So again, balik-balikon, gametocytes don't cause illness. They are not responsible for the symptoms of malaria. Again, they are not responsible for the symptoms of malaria because gametocytes do not multiply in the human host. They do not multiply in the human host. Instead, they are the form that gets transmitted to mosquitoes when they bite. So people who actually harbor gametocytes are what we call as carriers of infection or reservoir. Even though, meaning even though they might not show symptoms, they can pass the parasite on to the mosquitoes, which can then spread it to others. So this makes them important for the reservoir of infection. All right. So next. Okay, so let's break down the key factors that determine how malaria spreads from person to person. And we're talking about maturity, viability, and density of the parasite. So these are actually the game changers when it comes to transmission. So when you say maturity, please remember that only mature gametocytes are capable. Sorry, okay, I'll fix this. Okay, only mature gametocytes are capable of completing the malaria life cycle. So think of them like graduates. So only once they are fully mature, they can be picked up by the mosquito. So if they're still in their undergrad stage, they won't make the cut for transmission. So only the mature gametocytes. Next is viability. So when you say viability, it is essentially the health of the parasite. So if it's living. So if a parasite that's damaged or dead won't survive in the mosquito or the human host. So for transmission to happen, basically the parasite needs to be fit and alive, ready to continue its journey. So next is we have your density. This is all about the numbers. When you say density, numbers. So the higher the parasite's density in the human bloodstream, the greater the chances that the mosquitoes will pick up those gametocytes and pass them on. So these are just some of the factors that can affect the effectiveness of transmission of the infection. But quick note lang day, quick note. Humans can actually be carriers of multiple Plasmodium species at once. Meaning, it can it can actually affect how these factors would play out. So it's like having a variety pack of parasites, each with its own characteristics that can impact the transmission. So if humans can actually be carriers, so it would be harmful to both the mosquito and the succeeding victims of these mosquitoes as well. That is why we need proper control of this parasites. It's a cycle, man class. So in here, this is just a differentiation of malarial parasites. This is found in your essentials and in your panickers. So these are just the summary. So just take note. We have here number one, presence of hypnocytes, which are commonly seen in your Vivax and Novella, and relapse infection usually occurs in your Vivax and Novella. We have the recrudescence, we, very common to falciparum and to malariae. And we have here the certain periods of each life stages from erythrocytic to prepatent incubation. So let's proceed to the pathogenesis. So what happens when malaria enters the body? So what's going on inside your system when you get infected? So in here we have here the benign malaria. So for benign malaria, the hallmark or for benign malaria is actually anemia, splenomegaly, and paroxysms. So these are the hallmarks of a benign malaria. So you've probably heard of it before, but what does it really mean in the context of malaria? So when you say when you say hallmark, these are some sort of a triad symptoms. So these are your clues if the patient is actually infected or positive for malaria. So for anemia, so when the malaria parasite or the plasmodium parasite enters your RBCs, it starts to multiply, right? So it starts to multiply. And what happens when a red blood cell is infected? It bursts open. So it's like a balloon popping, and the parasites spill out into your bloodstream. And this is a very huge problem because your body now has fewer healthy RBCs to carry out the oxygen. So if your RBC would lyse, it would burst. There would only be fewer healthy RBCs to carry out the oxygen. And without enough oxygen, your organs can't function properly. And that is anemia. So you're left feeling weak, you feel tired, you feel exhausted. So that is anemia. So next, we have your splenomegaly. So splenomegaly, that is actually a fancy word for an enlarged spleen. So think of your spleen as the body's cleanup crew. So its job is to filter out the old, the senescent, and damaged and infected red blood cells. But in malaria, the spleen is actually overwhelmed. Why? Because it's working overtime to clear out all those infected RBCs that are being destroyed by the parasites. So, in this case, the spleen becomes swollen. So it becomes swollen, and this can lead to a condition what we call as the hypersplenism. So when we say hypersplenism, this is where the spleen starts trapping even healthy RBCs, making the anemia even worse. So imagine, just imagine, your spleen being like a janitor trying to clean up a huge mess, but the mess just keeps piling up. So that is why your spleen would become stressed, it becomes swollen, and it would lead to a condition called hypersplenism, wherein the spleen cannot identify clearly which is healthy or not healthy RBCs. So, meaning it cannot identify and distinguish the infected and uninfected RBCs clearly. That is why anemia become even worse. Okay, so next here is the paroxysms. So the paroxysms here, what we call as fever spikes. So fever spikes, meaning this usually happens in malaria. So these paroxysms are like a coaster of fever, chills, and sweating. If you remember that one, we have phases of your paroxysms, right? From the hot stage, the cold stage, and the sweating stage. So they actually happen because the parasites inside the RBCs explode. So when the RBCs explode, it releases toxins into your bloodstreams. So these toxins, your body reacts by triggering a fever. So it would trigger a fever. And here's the kicker, class. During the paroxysms, these paroxysms are cyclic, if you have remembered, right? So for example, for your Vivax and Ovala, the fever spikes every 48 hours. But with malaria, it's every 72 hours, meaning it's cyclic. So these are some of the triad or the hallmark of your benign malaria. So, aside from your benign malaria, we have also here a febrile paroxysm. So, this is this is just an explanation of what we discussed a while ago about paroxysms. So, febrile paroxysm are essentially the cyclic fever spikes, what we have mentioned a while ago. So, that is why your Vivax, Ovala, and your Foxiparum causes tertian malaria. Your malaria causes quartan malaria. Your Nolesi causes quotidian malaria. So, meaning this cyclic fever spikes occurs when the parasite bursts out of the RBCs, releasing merozoites into the bloodstream. So the release of your merozoites, if you remember your life cycle, it marks the end of the erythrocytic life cycle and it triggers the body's inflammatory response. So these paroxysms happens in three stages. So as I have mentioned, we have the cold stage. So the stage usually lasts from 15 to 1 hour, and it is characterized by a sudden onset of chills, intense cold, and rigor. What do you mean by rigor? That's the uncontrollable shaking. Now imagine you're being caught in an ice storm with no way to warm up. So that's what this stage feels like. And we have also here the hot stage. The hot stage, this is when the fever hits its peak. So usually the temperature rises dramatically to 39 to 41 degrees Celsius. So, and the person, this is when the person feels a dry burning skin. So the person feels like they're on fire. So the skin becomes dry and burning. And there's headache as well. So this is actually the body is trying to fight back the infection. So they're trying to control the spread of the parasite, but the fever is part of the battle. So if you go back to anatomy and physiology, every infection, the fever would really try to fight back the infection by increasing the body temperature. So they would try to increase the body temperature. This one way of fighting the infection. Next would be the sweating stage. So this is when the fever starts to subside. So it starts to subside and the body tries to cool down. So it's not just a slight sweat, it is profuse sweating. So it's like you've just run a marathon in a sauna. So it's like that. So this stage can last anywhere from 2 to 4 hours. So, and it's a sign that the body is finally regaining control. But the patient in here starts to feel exhausted and weak. But the worst part of the fever is already over. So, this is your paroxysm. Now, class, here's an important note that I want you to remember. Paroxysms don't always happen at regular intervals. Okay? So the timing can vary depending on the species of Plasmodium. As I have mentioned a while ago, Vivax, Valle, Falciparum, we have tertian malaria, we have um, quartan malaria for malariae, cotidian for Nowasi. But for Plasmodium falciparum infections, especially for Plasmodium falciparum severe infections, the fever pattern is often more irregular or even continuous. So there might not be the classic predictable paroxysms like the tertian malaria. So instead, patients with Plasmodium falciparum might experience persistent fever, often accompanied by marked prostration. Do you know what's prostration in your anatomy and physiology? prostration. Dili siya frustration class ha, prostration. So this is actually a state of extreme weakness and fatigue. So prostration. So if you're already feeling weak and fatigued because of studying, so you are in your marked prostration. So this is also very common in Plasmodium falciparum infection. And aside from that, you'll also see symptoms like headache and nausea, but these can be more intense and less predictable compared to the other types of Plasmodium. So that is why your Plasmodium falciparum is really different compared to the other remaining Plasmodium. So in here, for anemia, so we have already discussed anemia. We have already know uh, already know that it refers to a condition when there is a reduction in the number of RBCs, or in some cases, especially in the malarial cases, a decrease in hemoglobin levels. But in malaria, this type of anemia we see is normocytic and normochromic. So this happens or develops after a few cycles of fever. So right after your febrile paroxysm, if you remember, when your schizons eventually burst in your RBCs, releasing the merozoites, the patient would experience febrile paroxysms in these three stages, and then eventually anemia would develop after a few cycles of this fever. So this happens because of several key factors that I want you to understand clearly. So what we have here first is the parasite-induced RBC destruction. So class, when the Plasmodium parasite infects your RBCs, it causes them to rupture, right? It releases what again? It releases the merozoites into the bloodstream. So this direct destruction of RBC cells is one of the main contributors to anemia. But it doesn't stop there, class. The spleen, which filters the blood, removes not just the infected RBCs, but also the uninfected RBCs that have been tagged with immune complexes. This means, remember a while ago about hypersplenism, wherein in the splenomegaly, the spleen cannot distinguish anymore the infected from the uninfected. So, meaning the uninfected RBCs that have been tagged with the immune complexes, so even the healthy RBCs are being destroyed, further worsening the anemia. Okay? So next factor here is the bone marrow suppression. So the bone marrow, what is the bone marrow? What is the bone marrow for? What is the purpose of our bone marrow? What is the purpose? It is where the red blood cells are produced. So, the bone marrow, where red blood cells are produced, can be suppressed by the parasite. So, this results in decreased RBC production. So, meaning the body is not able to replace the lost RBCs quickly enough to maintain a very healthy circulating RBC. So, dili kaapas. So, your bone marrow cannot replace as quickly to maintain the healthy and mature RBCs. So, this is where another factor of your anemia comes in. Next, we have increased fragility of RBCs. So, the infected RBCs are often structurally weakened by the parasite's presence, making them more prone to rupturing. So if there's RBC feeding inside, if there's Plasmodium feeding inside the RBC, so their structures are oftenly weakened compared to the healthy RBCs, so making them more prone to lysis or breaking apart. And this leads to further loss of RBCs and could also contribute to anemia. And finally, we have your autoimmune lysis. So the immune system recognizes the infected RBCs and those coated with immune complexes as foreign. And this leads to the immune system attacking and destroying these cells, contributing even further to anemia. If you remembered, some of the healthy RBCs are tagged as foreign or as um, infected RBC. So these are coated with immune complexes. So this immune system would attack these cells and now contribute to further to anemia. So these are some of the factors. The last triad of our benign malaria is your splenomegaly. So a while ago we have mentioned basic information and context of malaria about the enlargement of the spleen. So basically, class, your splenomegaly is this happened because of the massive proliferation of macrophages. Why macrophages? So macrophages play a critical role in the immune response by engulfing both parasitized and non-parasitized RBCs. So your spleen has macrophages. It's just like na siya yung own soldiers or army. So these are the macrophages. The macrophages' role again is to engulf supposedly the dead or the dying, the infected RBCs. So usually, these RBCs are coated with immune complexes. It's just like a tag ba that would signal the macrophage that it is parasitized and ready to be engulfed. So, for patients suffering with malaria, the especially with severe malaria, there are too much RBCs that are infected. There are too much RBCs that are destroyed, and this leads to the spleen working overtime to filter and remove these RBCs, resulting into splenic enlargement. So this is an example of your spleen, splenic enlargement. So class, way back before, there are reports from tropical areas that describe patients with massive splenomegaly. And after ruling out other causes of splenomegaly, a condition was recognized in these regions, and we call that as the tropical splenomegaly syndrome, or your TSS, tropical splenomegaly syndrome. But over time, this was redefined as hyperreactive malarial splenomegaly. So, according to CDC, it is now recognized as the hyperreactive malarial splenomegaly, or HMS. Hyperreactive malarial splenomegaly, or HMS. So, this is the condition that is characterized by the hyperreactivity of the spleen. So I have mentioned a while ago that the spleen works overtime to filter and remove the infected RBCs. So, the hyperreactivity of the spleen in response to repeated malarial infections often lead to excessive spleen enlargement, just like this picture. Just this guy right here, this kid. Okay, so that is your HMS or your hyperreactive malarial splenomegaly. This is a real example of a patient undergoing splenectomy um, who suffered from malarial infection. Okay, so there are three key mechanisms that could actually help Plasmodium falciparum and evade the immune system and could cause a severe form of malaria or what we call as the malignant tertian malaria. So we have here the cytoadherence, the resetting, and then the deformability. So first we have the cytoadherence. When we say cytoadherence, cyto means cell. Adherence, the binding. So this is actually the process where the infected RBCs bind to the endothelial cells lining in the blood vessels. So your RBCs, the infected RBCs, would bind to the endothelial lining in the blood vessels. This is actually mediated. This is mediated by a protein called PFEMP1. What is PFEMP1? This is actually short for Plasmodium falciparum erythrocyte membrane protein 1. So this PFEMP1 allows the infected RBCs to stick to the blood vessel walls, preventing them from being filtered out by the spleen. So just imagine RBC, just draw your RBC sticking to the blood vessels wall. So if they stick to the blood vessel walls, they prevent themselves from being filtered out by the spleen and allowing the parasite to remain hidden in the deeper tissues of the body. So that is your cytoadherence. Next, we have here the resetting. So resetting is when the infected RBCs bind to uninfected RBCs. This forms a reset. So this forms a reset of cells. So just imagine reset. So infected RBC. Can I don't know how to draw. So one infected RBC would stick to another uninfected RBC. So this will form a reset. So this forms a rosette of cells, and these cells can prevent the infected RBCs from being cleared by the immune system. So, if there's a rosette of cells, this rosette of cells will not be cleared by the immune system. So, the formation of these rosettes is thought to increase the viscosity of the blood, making it harder for the blood to flow. So if there's a lot, just imagine imong RBCs clumping together, rosettes. So meaning, if they're clumping together, it would increase the viscosity of your blood. So if there's increased viscosity of the blood would have a hard time to flow. So this actually contributes to certain complications of your Plasmodium falciparum like your cerebral malaria. So some of the RBCs are being stuck there in the microvasculator or the blood vessels. So contributing to the complications of the cerebral malaria. So this is one way how your malignant Tertian malaria would undergo the process or the pathogenesis. And finally, we have here the deformability. So this actually refers to the change in the shape of the infected RBCs, deform. So there's actually a change of the infected RBCs. So normally, 'di ba, in your anatomy and physiology, RBCs are flexible. So if RBCs are flexible, it allows them to squeeze through tiny capillaries. However, in Plasmodium falciparum infections, the infected RBCs becomes more rigid and spherical, so solid, rigid. So meaning this rigidity makes them less filterable. So if there are less filterable, meaning they are less likely to pass through the spleen and are more likely to get stuck in the blood vessels of some internal organs. So these are some of the virulence factors of your Plasmodium falciparum that causes malignant tertian malaria. Now, let's talk about the serious complication of malaria. We have here a list of the complications that is caused by your Plasmodium falciparum malaria, but let's focus on your black water fever. So, black water fever is as severe as it sounds. Black water fever. So, it is characterized by hemolysis. So, hemolysis, if you remember, this is about the destruction of your RBCs. So, the destruction of your RBCs leading to the release of hemoglobin into the bloodstream. So, this hemoglobin right here, so if your RBCs are will rupture or will lyse, this hemoglobin is then filtered by the kidneys and excreted in the urine, giving it a distinct dark, almost black color, hence the name, black water fever. So, again, every time your RBC will burst, it would release the hemoglobin into the bloodstream, and then the hemoglobin will be filtered by the kidneys, and this will be excreted in the urine. And in the urine, it would actually give a very distinct dark, almost black color. Hence the name black water fever. So why does this happen? In Plasmodium falciparum malaria, if you remember, the infected RBCs are destroyed as part of the parasite life cycle, right? So the infected RBCs are destroyed. They would release the hemoglobin from these destroyed cells and they would overwhelm the kidneys. So when the kidneys are overwhelmed, they can lead to acute kidney failure. So the dark urine there is a key indicator of hemoglobinuria, meaning the presence of hemoglobin in the urine. Again, dark urine, key indicator of hemoglobinuria, presence of hemoglobin in the urine, which can also be a sign of renal damage. And this one of the more serious manifestation of malaria and actually requires immediate medical attention. So, black water fever is therefore a medical emergency. It can lead, if it goes on and on, it can lead to acute renal failure. It can also lead to severe anemia. And if not treated promptly, it could lead to death. So it is also a reminder why Plasmodium falciparum malaria is particularly dangerous jud when it causes malaria, and it can cause severe complications very quickly. Okay, so here we have conditions often arise from the body's prolonged response to the parasite, and this is what we call as chronic complications of malaria, meaning this highlight just how serious the long-term effects of malaria can be. So I have already discussed this bullet number one. We have tropical splenomegaly syndrome. So, if you remember, this is the condition which results from an abnormal immune response to repeated malarial infection, especially in endemic areas, which is now labeled as the HMS or the hyperreactive malarial splenomegaly. So that is your TSS, tropical splenomegaly syndrome, also known now as the hyperreactive malarial splenomegaly. Next, we have the quartan malaria neuropathy. So, your quartan malaria neuropathy is linked to what? Plasmodium. is often linked to Plasmodium malariae infection. Quartan, man. It's quartan. So just remember, it is linked to Plasmodium malariae infections. So this is usually a condition involves immune complexes that damages your renal glomeruli, neuropathy. Neuropathy. So it damages the renal glomeruli, leading to kidney dysfunction. So over time, this can result to chronic kidney disease and even kidney failure if not managed properly. Lastly, there's the association between malaria and Burkitt's lymphoma. So you would know this, you would meet Burkitt's lymphoma in your hematology. So I will not be talking more about the lymphoma, but I would be talking how malaria promotes Burkitt's lymphoma. Take note that malaria doesn't directly cause this cancer, huh? So malaria doesn't cause directly this cancer, but it plays a role in promoting the cancer. So when a child is infected with Epstein-Barr virus, which is a common virus in areas with high malaria prevalence, and which is the cause usually by, which is the causative agent of Burkitt's lymphoma. So when a child is infected with EBV, right here, the immune suppression caused by the repeated malaria infections can increase the risk of developing Burkitt's lymphoma. Burkitt's lymphoma is a form of a non-Hodgkin lymphoma, which you will know later in your hematology. So this is just this third bullet right here is just a tragic reminder of how the immune system's vulnerability to malaria can make the body more susceptible to other infections and cancers. And this is not just true to malaria. So if your immune system is vulnerable, it would be more susceptible to other infections. Okay? So, um, I think I would stop my lecture video here and I would continue to recording to another video. So for the laboratory diagnosis.